Question 1. The following question explores features of composite trigonometric functions such as sin x, sin x. Suppose Sn of x denotes the function sin x composite within itself. N minus 1 times defined for n greater or equal to 1. N is a positive integer where x between 0 and 2 pi. For example, S1 of x equals sin x and S sub 2 OX equals sin x. On the same axis, sketch the label the graphs of y equals s sub 1 OX and y equals s sub 2 OX. On your sketch, show the values of the intercept with the axis. Okay, we're gonna first graph sin x and then s sub 2 OX equals sin x. Okay. Yeah, it is almost same. Actually, the blue one is sub 2 and the red one is sin x. We can say that this one is let's say it is sin x, and I know that here is 0 pi and 2 pi, and the other one, the blue one, is sub 2. It's gonna be a bit below than red one. Okay, so I will draw it like this. Yeah. So the both of them is x-intercept is same, and the y-intercept is 0 in this case. Yeah, we draw it. Sin x. The next question, determine the maximum value of S sub 1, S sub 2, and S sub 3. Okay, the maximum value for S sub 1, you can say that maximum value it's gonna be 1, right? Yeah, this is 1. And for the blue one, it's gonna be 0.841. 0.841. For S sub 3, we can also draw that one. Yeah, the green one. So the maximum value is 0.746. Let's say 0.746. Yeah. Next question is find the least value of n for which the maximum value of s sub n x is less than 0.6. Okay, we can just copy this one and write at the beginning sign again. Yeah, this one is, let's check it. Okay, still we need to write sign again. Let's write sign again. Yeah, the black one is, yeah, we need more. Now, this one, yeah, this is 1, 2, 3, 4, 5, 6. We can write to here. It is S sub x, and we found it 0.587. 587, which is less than 6. The next question is by considering this is the S sub 2. By considering the equation dy over dx equals 0, show that there are exactly 2 points of 0 gradient, one at x pi over 2 and 3 pi over 2. So we're gonna find the derivative of this function. S sub 2 equals sin x, right? Let's call it y. And the derivative of this function will be cosine sin x times cosine x, because I know that the derivative of the inside is gonna be cosine x. And when we draw the graph of this function, let's check it. So this is the graph of this function, and the 0 will be pi over 2 and 3 pi over 2. We can draw this one directly. Yeah, like this. This is pi over 2 and 3 pi over 2. The next question is the derivative s sub n of the differential of this function can be expressed as a product of cosine functions as follows. This is like the function. He showed that s sub 3, the derivative of s sub 3. Okay. So we will just replace n with 3 in this expression. It's already given us. In this case, we're gonna write in here cos s sub 2 x times cos s1 x, right? And then cosine x. That's it. So I know that S sub 2 is sine x, and S sub 1 is just sine x. Yeah, this is like this. Yeah. And the next question is, use mathematical induction to prove that for all n. Okay, this rule, we're gonna prove the rule by using the mathematical induction. Okay, let's write this one again. We can start by using for n equal 1. Let's write it. It's gonna be the derivative of this function, right? And I know that s sub 1x equals sine x. In this case, s sub 1x equals derivative of this function, which is cosine x. Okay, because I know that s is decreasing by 1, and at the end of the terms it will be actually 0, s sub 0, which will give us cosine x. We can say that for n equal 1, the statement is true. The statement is true. Now we can say that, assume that for n equal k, the statement is true, which is as the derivative of f sub k equal x cosine s. Yeah, this one. Yeah. Now we're gonna show that it is also true for n equal k plus 1. Consider for n equal k plus 1, which is the derivative of f sub k plus 1 ox, right? What is this? I know that uh, s sub k plus 1 is gonna be sine s sub k ox, right? Because s sub k is uh, the k terms of sine x. And we will look for the derivative of this function or expression. So how we're gonna write the derivative of this expression? First, the derivative of sine will be cosine s sub k ox times the derivative of inside. This is the chain rule, right? Yeah, the derivative of s sub k ox. And we assume that this is true in the previous expression. From here, we can say that the derivative of s sub k plus 1 ox equals cosine. We're gonna write the same actually. Yeah, this one. In this case, we can say that it is shown that the statement is true for n equal 1 if it is true for n equal k, then it is also true for n equal k plus 1. Therefore, the statement is true for all positive integers, right? The next question is, use L'Hopital rule to show that limit x approach 0 s sub n of x divided by x equal 1. Okay, x approach 0 and our function is s sub n of x divided by x. When we substitute 0 into this expression, we're gonna see that uh, this is s sub n of 0 divided by 0, which is 0 divided by 0, and we can apply now the L'Hopital rule. So the derivative of the numerator will be, is given that in the previous question here, is given in the question, so I will just write this one. It is cosine s sub n minus 1x times cosine s sub n minus 2 ox times cosine x, and the derivative of the denominator is 1. In this case, we will just plug in 0 into the numerator. Since all the functions is cosine, and I know that cosine 0 equal 1, right? we will have here 1. And in parentheses, I know that s, for example, any sub n minus 1 minus 2 will be 0 because sine 0 is 0. In this case, we will get 1 from all of these terms, and the numerator will be 1. 1 over 1 equal 1. Second question is given absolute value of x is less than 1. Find the sum to infinity of the geometric sequence 1 minus x squared plus x to the power of 4 minus x to the power of 6. Okay, and it asks for minus 1 minus x to the x squared plus x to the power of 4 minus x to the power of 6, and it goes to infinity like this. We can write this one in terms of minus x squared. Why? Because 1 plus, let's say, minus x squared to the power of 1 plus minus x squared to the power of 2. It gives us, as you see, x to the power of 4, the same. And the fourth term is minus x squared to the power of 3. As you see, it is also minus x to the power of 6. Okay, we wrote this one in terms of minus x squared. In this case, we can say that the common ratio in here, this is the geometric sequence, and the common ratio is minus x squared. So what is the formula when it goes to infinity? It is 1 divided by 1 minus r. In this case, it will give us 1 divided by 1 minus x squared equals 1 over 1 plus x squared. So this series will be equal to 1 divided by 1 plus x squared. Okay. At the next question, is use integration to show that the Maclaurin series of arctangent x may be expressed as arctangent x equals, this expression. Okay, when you look at these terms, x minus x to the power of 3 divided by 3 plus x to the power of 5 divided by 5, you can notice that this is the integral of the terms that we wrote in the previous question, right? In this case, we will just will look for the integration of these terms. I will write the integral of the previous question, right? It's going like this, and differential of x equals integral of 1 over 1 plus x squared. Okay, if you found the integral of left hand side, we will see x minus x to the power of 3 divided by 3 plus x to the power of 5 divided by 5 minus x to the power of 7 divided by 7 is going like this. You can add, by the way, the constant value c, but it's not important in here because we will also have the constant value at the right hand side. And the integration of this expression, it is arctangent x. Okay, yeah. So we prove that. Next question is x equals 1 divided by square root of 3 and the first three terms of the Maclaurin series of arctangent x. Find an approximation for pi to 3 decimal places. Okay, in the previous question, we wrote the Maclaurin series of arctangent x, and we're gonna use just first three terms. I will write until here, and then I'm gonna replace x with 1 over square root of 3. So if you replace x with 1 over square root of 3, we're gonna find which angle it will be equal. Yeah, plus to the power of 5 times 1 over 5. And I know that arctangent 1 over square root of 3 is pi over 6, right? Because tangent pi over 6 equals 1 over square root of 3. And I can write the remaining same, this one. So we are looking for the approximate value of the pi. In this case, I will multiply both sides by 6 to find this value. Okay, I can write 1 over 3 square root of 3 times 1 over 3. It's gonna be 1 over 9 square root of 3 times 1 over 5. Okay, yeah, let's find this one. Yeah, it is approximately 3.16. 3.16, yeah. But it says three decimal places. In this case, I will write 3.156. 3.15 and 6, yeah. Next question is the Maclaurin series of arctangentics is an example of an alternating series, a series where consecutive terms are positive and negative. Consider the following theorem. The theorem is for alternating series with terms of decreasing magnitude. The error obtained in using a finite number of terms is less than or equal to the absolute value of the next term in the sequence. Using the theorem, the maximum error in using the first three terms as an approximation to arctangent x is given by magnitude of minus x to the power of 7 divided by 7. In other words, in the absolute value of arctangent x minus the first three terms, as you see from here, less or equal to the fourth term. Determine how many non-zero terms of the series will need to be used such that the error in approximating arctangent 1 over square root of 3 is less than 0.0001. In other uh, words, 1 or 10 to the power of minus 4. Okay, now we're gonna check first what's the fourth term uh, when we replace x with 1 over square root of 3. Okay, so the error you can write uh, x absolute value of arctangent x minus, let's check it, x minus x to the power of 3 divided by 3 plus x to the power of 5 divided by 5 is gonna be greater less or equal to minus x to the power of 7 divided by 7. And if you look for the first uh, fourth term, okay, we're gonna write this one. In this case, the error will be less or equal to x to the power of 9 divided by 9. So we can just calculate this one. When x equal 1 over square root of 3, it's gonna be, let's calculate this. It is 0.003, the error 0.003, right? So when you replace this one with 9, the error will be approximately, let's write 0.00079. Let's check it again. Yeah, it's gonna be that. So we still need to add one more term to this one. Arctangent x minus x to the power of 3 divided by 3. I'm writing so the first fifth term, right? In this case, it's gonna be less or equal to x to the power of 11 divided by 11. And let's check the error. Yeah, this is again greater than the value that we are looking for. We can write approximately like this, or 1/6 more. So when we add one more term to this one to find the error, it will be less or equal to the power of 13. Okay, I'm gonna check this now. Replace 11 with 13. So this is the value that we're looking for. We can write in here, it is approximately 0.00006, right? Yeah, 0.9. Yeah. In this case, how many terms we use 1, 2, 3, 4, 5, 6. 6 terms. Should we use, we can write 6 terms need to be used. Yeah. The next question is, by using integration by parts, show that the integral of arctangent x from 0 to 1 over square root of 3 equals pi divided by 6 square root of 3 minus 1 over 2 times ln 4 over 3. Okay, from 0 to 1 over square root of 3, I'm looking for arctangent x. Um, I will first equate arctangent x to u and the dx equal to dv, right? What's the integration by parts? It's gonna be u times v minus integral v times du. When we first define the differential of to the both sides, the left-hand side will be 1 over 1 plus x squared dx equals du, right? The integral of the x and the dv will be x equals v. In this case, I will write this integral, which is arctangent x, u times v, it is arctangent x times x, minus integral v times du, which is x times 1 over 1 plus x squared dx. Okay, if you look for here and replace 1 plus x squared with u again, from here you can say that the derivative of the left hand side will be 2x times dx equals du. Okay, so we are making substitution actually, and which means x times dx equals du over 2. From here you can say arctangent x times x minus uh, integral of, let's say, uh, du over 2 times I replace 1 plus x squared with u. So it will give us, I know that the integral of 1 over u will be ln u over 2, right? And you can replace u with again 1 plus x squared, 1 plus x squared divided by 2. So this is the solution of the integral arctangent x. And we have the limits from 0 to 1 over square root of 3. In this case, you can write from 0 to 1 over square root of 3. And when you replace x with 1 over square root of 3, you're gonna see arctangent 1 over square root of 3 times 1 over square root of 3 minus ln in parentheses 1 plus the square of 1 over 1 divided by square root of 3 will be 1 over 2 divided by 2. And when you replace x with 0, we will get 0. Yeah. And I know arctangent 1 over square root of 3 is pi over 6. Okay. And ln 4 over 3 divided by 2. Yeah, we show it. This is the expression that we need to show. The next question, determine the value again from 0 to 1 over square root of 3. The integral of, actually, this is the 1, 2, 3, first four term of the arctangent x. This is the Maclaurin series. We can write it again. Okay, from 0 to 1 over square root of 3 x minus x to the power of 3 plus divided by 3 plus x to the power of 5 divided by 5 minus x to the power of 7 divided by 7. You can directly write this to your graphing calculator. When you write this expression into the calculator, you're gonna find 0. Let's copy this one. Yeah, because it's asking for to write 6 decimal places. Let's check it again. Yeah, 6 decimal places. Yeah. Use the results in parts E and F to find an approximation for pi. Give your answer to 4 decimal places. Okay. For example, at equation E, we found that the integral of arctangent from 0 to 1 over square root of 3, this value, okay? And we can say, actually, this expression we found in the question E is equal approximately to the solution that we found in F because this is 1, 2, 3, first, fourth term of the arctangent. We almost doing the same integral in both questions. So we can say directly that this is the approximate value of this expression will give us 0.158 422. And from here we can find the approximate value of pi, right? Because pi over 6 times 1 over square root of 3 will be approximately this value plus ln 4 over 2 divided by 2, right? From here you can also say pi will be approximately 6 times square root of 3 times this value plus ln 4 over 3 divided by 2. Let's find the approximate value of pi. Okay, this is approximately 3.1412. 1412, yeah. Next question is the integral of, as you see from here, 1, 2, 3, 4 terms may be considered as the sum of alternating terms. Hence, this integral can be written in the separately of each terms, right? And the integral of arctangent x is approximated using the sum of the first four definite integrals. Verify that the theorem used in part T holds in this case. Let's remember what was the theorem. This one, okay. At the part D, we use, for example, in here the first three terms, and it's the less than the four terms. In this case, I will take this one, or let's use the theorem if it is right or not. In this case, I will write here arctangent x minus the the first four terms, x minus x to the power of 3 divided by 3 plus x to the power of 5 divided by 5 minus x to the power of 7 divided by is gonna be 5 and 7. Okay, it will be less or equal to x to the power of 9 divided by 9. Yeah. We can also plug in the integral sign into the absolute value in here. So it will be the integral of this expression, okay? And I can write, for example, the first, let's say, and our limit is from 0 to 1 divided by square root of 3, 1 over square root of 3. In this case, we can find the integral of first arctangent x dx minus from 0 to 1 over square root of 3 this integral, right? Yeah. So let's check. We found in the previous question the one with arctangent x. This is the answer. We can copy this one. I will write and subtract from this to the value that we found in the previous question, which is 0. Yeah, 0.158422. Okay, and we will also find the integral of this expression. And when you write the integral of this expression, you're gonna find 0. 0.000457. Yeah, and let's find this expression again. Yeah, it is 0. Is less than the other one, right? Yeah, 0.00003 and 369. Yeah, this is less than the other one. So which means the theorem, meaning the theorem used in part D holds in this case. The last question is suppose that the maximum error in approximating the integral of arctangent x is from 0 to again 1 over square root of 3 is required to be at most 10 to the power of minus 6. Determine the smallest number of terms of the Maclaurin series for arctangent x that should be used. Mm. Yeah, in the previous question, we found that, as you see from here, the integral of arctangent x, for example, for the four terms, the first four terms, the error was less than this value. In this case, we are looking for, again, for the same function, arctangent x, and how many terms do we need to write in here to make the error less than 10 to the power of minus 6. As you see from here, if the function or the expression is x to the power of 9 divided by 9 for the approximate error, we found this one 0.00000457. So we still need to uh, increase the degree in here. And so if I make the power 11, and the value will be, as you see from here, again, is not less than 10 to the power of minus 6. So I will increase or replace 11 with 13 now. And if you replace this value, the integral will be this one. We can write this one. Possibly the next value will be less than the number that we look for. In this case, we can write to here, if the power is 13, the approximate value of this integral will be, let's check it, it was, yeah, it's gonna be 0 or 2.512 times 10 to the power of minus 6. So I will increase the power to the 15, and let's check this integral. So this integral will be, yeah, 6.35 times 10 to the power of minus 7, which is less or equal to 10 to the minus 6. In this case, we can say that mm, from this integral, we need to subtract first. Let's check it how many terms. We do not forget to add the x for the each integral. Yeah, this is 1, 2, 3, 4, 5, 6, 7. Okay. If we write the first 7 terms, then we can say that the error will be uh, less than or almost 10 to the power of minus 6. Yeah, 7 terms should be used. We can write should be used. Yeah, we done all of the questions. Thank you very much for watching. If you need any help, please leave a comment in the comment section. See you in the next videos. Take care. Bye bye.